Hello, my name is Matthew Key, and my team is analyzing and simulating a drone for our MAE152 final project. I studied the grabbing mechanism while Yuki-Hu analyzed the propellers, Fortino Vargas focused on the arm, Aaron Yang focused on the landing legs, and Joan Yang examined the body. In my analysis, I assume the drone carries a 150-pound load that shifts due to wind or external forces. I varied the boundary conditions to assess tensile and compressive loads on the hook, while the drone is fixed inside the top circle to simulate an interference fit. The initial design showed yielding at the junction between the top circular section and the hook. To improve force distribution, I increased the curve radius at these points. In the second iteration, I reduced the part's width to minimize weight, a critical factor for aerial vehicles. I performed an SN curve analysis assuming each cycle corresponds to a package pickup and drop-off with 50 cycles per day. The final design lasts approximately 1.37 years, while the first iteration lasts about 4.1 years. Depending on the drone's expected lifespan, the first iteration may be preferable.
And for the propeller will be made of carbon fiber with data developed based on online research. The boundary condition assumes that each system can provide over 20 Newton lift with heel fixed and factored by upward airflow. In another case, the propeller experiences a downward force from the drone's weight. Collision effects are primarily considered at blade edge, particularly the vertex, and vertical force affected by propeller's mass. Since the propeller is a rolling state when working, the effects of torque and centrifugal force on hub also need to be considered. Initial designs will favor blade consideration for some fewer points, leading to high stress consideration. After switch the to three blades and increase thickness by 0.2 millimeters, I expect to improve force distribution, but the results shows greater maximum displacement and stress in most cases. The design changes increase stress and displacement, but balance force distribution at the hub. The next design iterations will focus on uh, alternating the blade shape, increase the arc, and rotating the edge, which has results in lower maximum stress and displacement.
Our drone arm is subjected to three main load cases: lift and thrust during flight, landing impact during touchdown, and static end load from motor's weight and torque. We applied a 100 Newton distributed lift force, 180 Newton landing impact force, and a 190 Newton static load with a 1.5 Newton meter torque at the motor mount. The arm is fixed at the chassis, and we use aluminum 661 T6 for its lightweight and strength properties. The boundary conditions ensure we capture realistic loading scenarios, including both concentrated and distributed forces. For initial design, we saw high stress near connection points. In our first iteration, we added 2 mm fillets as stress concentrated areas, but instead of reducing stress, it increased due to reduced stiffness. In the second iteration, we introduced 3 longitudinal ribs along the arm's length while keeping the fillets. This significantly lowered displacement and stress while increasing stiffness. Frequency analysis also showed improved structural integrity as seen in the results table. To validate our FEA results, we performed a closed form beam analysis for a concentrated landing impact at 180 newtons. The theoretical calculations assume a uniform beam, simplifying the geometry. However, our arm is tapered, leading to a large percent error, around 299% for displacement and 353% for stress. This highlights the importance of FEA for capturing complex geometries more accurately. The closed form analysis still provides a useful baseline for comparison.
Welcome to the analysis of mainframe body. The purpose of this redesign is to reinforce the body frame to strengthen it. The body boundary conditions for the landing impact are 120 newtons acting around surrounding the body frame bottom, and the whole frames are fixed at the screw thread because the body are connected with screws. For the static component load, the fixed are at the arm since the drone remains static in air and the motor from arms are supporting it. Here's my body analysis and result. And here is the result of my simulations. As a result, we can see that the second design iterations are overall better in performance. The maximum displacement are almost the same as my first iterations, but the maximum stress are significantly lower than my first iteration. It means that we'll increase the body structural strength. It also increase the flexibility of the whole body frame. So the maximum stress are lower.
Hello everyone, this is Aaron Yan. Today I will present the design iterate of the landing leg. Our goal was to reduce stress at the leg connection points and to make it stable and reliable. Our simulation load will be 10 Newton because it is the average of drone weight. And here is our setup. Our first boundary connection fixed restricting under the leg support, and our second boundary condition is fixed at the end of leg. And the first design used ABS material but has no support at the leg, as you can see. Here, where it touches the surface, this causes high stress in the small area, which could lead to failure over time. To solve this, I made the connection area 1 mm thick. To spread out the pressure, it helped, but the stress moved to a curve of the leg instead. So I designed the second one. I added the angle support between the leg and the connection. This helped distribute the stress more evenly and made the leg more stable. And here the stress is much lower overall, improving reliability. By making those changes, the design is now stronger and more stable.
In conclusion, this project teaches us to analyze the drone structural component, assess failure risk, and implement design improvement. Key optimizations include reinforcing joint, enhancing impact resistance, and minimizing stress concentrations to ensure reliability in high-stress conditions. We will refine our design through simulations and testing, focusing on durability and performance. Thank you for watching. That's all.